Hi, in this video, what we're going to talk about is relative motion. So first, I'm going to show you some examples of relative motion that I took totally unsafe in my truck, driving down Military and driving the expressway coming to work. But it shows my frame of reference looking at a truck that's moving, or looking at the background, or looking at other different things. So you're looking at how things are moving from different perspectives. Okay, so I'm going to show you those examples first. In all of these examples I'm going to show you, you're going to be in my frame of reference, which is inside the moving truck. Okay, in this first one, we're in the truck moving relative to the earth. And you can tell that because you can see in the background stuff is moving by. In the second example, me and the big dump truck next to me are moving at the same speed relative to each other, but we're both moving relative to the earth. So we look like we're still to each other, but you can see in the background we're moving relative to the earth. Okay, in this third example, it's a little bit harder to tell because you can't see the background anymore. If you look carefully, you can kind of see tires moving, but am I moving? Is the big truck next to me moving? Or are we both moving, right? Or if you couldn't see the tires, are we sitting still? It's a little bit harder to tell without having that earth frame of reference there to see. Okay, this next one is a little bit harder because now there's really nothing. So at first, I'm sitting right next to the big truck, right? But are we both moving? Am I moving? Am I speeding up? Or is the truck slowing down? Am I going forward, or is the truck moving backwards? Okay, in this fifth example, I'm driving the same speed next to this truck. So did I hit the brakes, or did the truck speed up? Am I going slower, or is the truck speeding up faster? And the answer is, I think you may have been fooled. We're not doing anything. I was parked next to the truck, right? And you can see that I'm in the H-E-B parking lot. So the question is, could you tell from my frame of reference, did I back up, or did the truck move forward? Okay, so like I was saying in those examples, the thing to remember with this is all motion is relative, right? So even right now, you're sitting maybe on a desk or on your bed in front of a computer, and relative to the earth, you're not moving, right? Unless you're watching this in the car. But relative to the earth, if you're sitting on your bed watching this video, you're not moving. But relative to the sun, you are moving, right? So the earth isn't sitting still. The sun is in outer space, and the earth is orbiting around the sun, right? So relative to the sun, the earth is moving like 100,000 meters per second, which is pretty fast. You don't feel that though. So even from the earth's rotating perspective, right? So the earth is rotating about its axis. So even though you're sitting on your bed and you feel that you're moving 0 meters per second relative to the earth, in reality, the earth itself is rotating at about 1,000 miles an hour. And that comes out to, that's about 450, 460 meters per second. So right now, if this is east, right, you are traveling that way at 1,000 miles an hour because the earth is rotating, right? So all motion is relative. So when you say this thing is moving, we have to specify what it's moving relative to, right? So the whole example with the trucks, you have to say what the motion is relative to. So if I'm driving right next to the truck, my motion relative to the truck was 0, but my motion relative to the earth was some positive velocity. Okay, so what I'm going to show you now is a clip from a video that shows relative motion from 2 different reference frames. So first you're going to watch an object that's moving on a track where you're on the track moving. And then you're going to watch from the Earth's frame of reference as a track moves, but somebody pushes the ball forward. And then it's going to be moving the same way, and somebody's going to push the ball backwards.
Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards? I'll try. If Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now we are on a car here, a car which can move and which really is going to move in this direction. And we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is, the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind.
Okay, so you should have seen, like they were saying, when you were in the Earth's frame of reference, there was a noticeable difference in the speed of the little puck when it was going with the motion of the track and when it was going against it, right? So it's the same motion. When you were sitting there on the track with them, the puck looked the same back and forth because you were in that frame of reference. But now when you're in the fixed Earth frame of reference, when you see something moving, it either got faster or slower relative to you. This would be a good example of this. Instead of a track and a car or a little puck, imagine a school bus, right? So you're standing here watching a school bus go by. So let's say I'm standing here watching the school bus go by. So if I look at this person in the bus, I look in the bus and I see a person, the bus is going 3 meters per second, that's really slow, whatever. And the person in the bus is walking 1 meter per second towards the front of the bus. I see that person in the bus as going faster than the bus, right? Because I'm getting the bus's speed plus I'm getting the speed of the person. So in this case, if you're in the fixed frame of reference and you're watching two things that are together moving, in this case, it's going to look faster. So I'm going to see the person going 4 meters per second. Okay? But now let's say I look at somebody else in the bus. I look at somebody in the bus that's at the front and they're walking to the back of the bus. Like, never mind, the bus driver shouldn't be driving when the person is walking, but whatever. So this person is walking to the back of the bus. So I'm going to see this person as going slower than what the bus is actually going. Because as the bus moves, like, think about that. As the bus moves, this person is walking backwards in the bus. So they're taking away some of that speed. So in this case, I'm going to see the person as going 2 meters per second towards the back of the bus. So that's from the fixed Earth frame of reference. And all of these, they're not so hard to do if you put yourself in the frame of reference that you want to be in, and then you think about, okay, what would happen if I'm looking at that? So next, we're going to look at an example of being in a moving frame of reference and looking at something else. Okay, so now let's look at an example of a moving frame of reference. So pretend you're walking in the hallway at school when coronavirus wasn't a thing and we could all wander around and not wear masks and stay 6 feet apart. So you're walking down the hallway, right? And let's say you're going 2 meters per second. And there's two people in the hallway. So this person is walking towards you also at a speed of 2 meters per second. And then there's another person up here who's walking a little bit faster than you at 3 meters per second. Okay, so how do these look relative to you? So it's a little bit different now. In the fixed frame of reference, you could just add or subtract. But in a moving frame of reference, again, there's a whole bunch of stuff you could do where if you add vectors, but I'm trying to teach you to think about it conceptually, like what's happening. So imagine you're this person. If you walk towards somebody who's coming at you, right? What's going to happen is you're going to look faster than you would to somebody who is standing still. Have you ever been in a car and when you drive by, like in the left lane, if you're going 40 miles an hour, somebody else is going 40 miles an hour, when you two pass each other, you look really fast, right? In reality, you look like you're going 80 miles an hour to each other. Because if you're both in a moving frame of reference, relative to each other, those speeds add up. So it's going to look faster. So if this is you, let's say this is, I'm going to call this person A and this person B. So relative to person A, you look like you're going faster. So you look like you're going 4 meters per second. So this would be the same. You would see each other the exact same as if this person was going 0 meters per second and you were going 4 meters per second, right? Because all speeds are relative. Everything has to match up. So let's look at B now. So B is going 3 meters per second. So he's going a little bit faster than you. But if you've ever been with people in a hallway, right? If you're going one direction, the other person's going the same direction, y'all look slower than each other, than you actually are walking, right? So if you were walking the same speed, like the example when I was in the car, if you're walking right next to somebody, that's the same thing as if you were just standing there, not moving relative to the earth and talking to each other. If you walk at the same speed and talk relative to each other, it's still 0. So when you go the same direction in a moving frame of reference, these are going to look slower. And so if they're going to look slower, you're going to subtract. So for B, it's going to be 3 minus 2. So you're going to see each other going 1 meter per second. So in reality, what's going to happen? This person's going a little faster, right? So your 2 meters per second that you're going forward is getting canceled out by 2 of his. And it's left over with 1 here. So you see this person as going 1 meter per second this way, right? It's a little bit faster. The whole key is, with all relative motion, the motion that you see in one reference frame, so you have to see this person as the same that they see you in their reference frame. That's the whole key with relative motion. Whatever A sees B in his reference frame, B has to see A in his reference frame. That's the whole key to this. All motion is relative, but those numbers all have to add up and it has to make sense across all the reference frames. So we're going to do some examples like this. Okay, so I'm going to walk you through solving the first row of these relative motion problems. Okay, so what you have is a bunch of things moving, and the hitchhiker down here is not moving. So this is the Earth reference frame. Right, we're calling not moving relative to the Earth. That's our 0, and all these other things are moving at these speeds and in those directions relative to the Earth. Okay, so first off, when you go fill these in, this is your frame of reference that you're going to be in, right here, this column. So you're going to be in the car, you're going to be on the river, you're going to be in the boat, right? And these are the things you're looking at from this frame of reference. All right, so if you're in the car and you're looking at another person in the car, you see each other going 0 meters per second because you're both in the same frame of reference. So all of these, river, river, boat, boat, all of these down the middle are all 0. Because if you're in the plane, even though you're flying 490 miles an hour relative to the Earth, if you're sitting in the plane relative to the person sitting next to you, you're going 0 meters per second, right? Relative to the Earth, yes, you're going 490. But relative to the plane itself, you're going 0. Okay, so those are all 0. All right, so let's start with the first row, car. If you're in the car looking at the person in the river, all right, so here's the car, here's the person in the river. This is like the example when you walk by somebody in the hallway and they look like they're going faster than they are. So if you're going past the person in the river, if you're going 30 and the river's going 6, you're going to see each other as faster, which means you're going to see each other at 36 miles per hour, right? Because if this was 0, it would be 30. But now this one's going 4, so his 4 is adding to yours from your reference frame. And then to get the direction, the easiest thing to do, I found, is just imagine yourself sitting in the car, and then which way would you have to look to follow that object, right? So if I'm in the car and the person in the river is going this way, as I'm driving by in the car, I'm going to have to turn my head this way to follow the person floating in the river. So instead of saying left or right or anything like that, I'm just going to draw an arrow. So if you're in the car, you see that person in the river going 36 miles an hour this way. All right, so car and boat. So here's the car, here's the boat. So now they're going the same direction. So this is like the example where if you pass by somebody slower than you in the hallway. So like here's a person walking 1 meter per second in the hallway. And here's you walking 2 meters per second. When you pass this slower person, 1 of your meters per second basically cancels out, because it's like if you were walking right next to somebody in the hallway at the same speed, you would both look 0. So 1 of them cancels out and you're left with the 1 extra that this guy has. So in reality, when they're going the same direction, you can think of it as they subtract. So you're going to look slower when 2 things move in the same direction. So that car going 30, the boat going 2, the 2 of the boat gets canceled out, and so you're left with the car going 28. And then imagine you're in the car. Which way do you see the boat? Well, if I'm driving by the boat, I'm going to have to turn my head this way to watch the guy in the boat as I drive by. So again, it's left. All right, so car, runner, opposite directions look faster. So 30, 4, 34. In the car, which way do I have to turn my head to follow the runner? As I'm driving by, I have to turn this to follow the runner. So, again, that way. Okay, so pause the video, you try the hot air balloon in the plane. So, in the car, looking at the hot air balloon, in the car, looking at the plane. Pause the video, you try it. Okay, so you should have got, for the car and the hot air balloon, same direction, so they look slower. So 33, that's 27. And again, you're looking at the balloon, you're going to have to turn your head this way. And if you're in the car looking at the plane, they're going opposite. So it's going to look faster. So 490 plus 30 is 520. And again, if you're in the car watching the plane, you turn your head this way to see it. So there's the first row. Okay. You try the second row for the river. Okay. So these river, car. So if you're in the river looking at the car, opposite, faster, 36. And if I'm in the river looking at the car, now I'm in this perspective, so I have to watch the car go this way, right? So the car sees the river go this way, but the river sees the car go the opposite way, right? And so you can kind of pick up on a pattern here. These numbers have to be the same. If I'm the river looking at the car, I have to see the car from the river's perspective at the same speed. Right? These numbers can't be different because these 2 things are watching each other. The relative speed has to be the same. But the direction is changing. So like, as you drive by, the car watches the river go that way. The river's in the opposite perspective. He's going to see him go the other way. Okay? And so the rest of these river boat. So 6, 2, opposite. So it's 8. And the river is going to watch the boat go that way as it passes. River, runner. So river, 6, 4, same direction. So it's going to look slower. So that's 2. And as the river passes, the guy in the river passes the runner, he's going to have to turn his head that way to follow him. River, hot air balloon. So 6, 3, opposite direction. So it's going to be 9. And again, the river, turn his head this way as he passes to follow the balloon. And then river, plane. So plane's going this way, river's going this way. So now this one's a little weird. They're both going the same direction, right? So it's going to be slower. So 496, that's 484. But now that's going faster than you, right? So if you're in the river, here's you, that plane is zooming by. So if you're in the river, you're still going to have to turn your, even though you're moving this way, you're still going to have to turn your head this way to follow the plane. So it's going to be 484 that way. Okay, so you pick 2 more rows and you finish those on your own, and that's what you're going to turn in to me. So you should submit a picture of this thing with 4 total rows done, since I've done 2 for you.
What's happening this time? Why doesn't the puck move straight across the table as it did before? As you can see, it doesn't. So, if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless. So what can be exerting this unbalanced force on it? Suppose that you watch the motion, this time, through a camera which is fixed in the Earth's frame of reference. I think if you concentrate on watching just the puck, you can see that it is moving in a straight line, and that therefore there is no unbalanced force acting on it. I don't know about you, but I'm dizzy.
Now, I said that the Earth was rotating about its axis. How do we know that this is so? Well, if you take a time exposure photograph of the stars, they seem to be moving in circles about the pole star. But all motion is relative. Is there any way of telling which is moving, the Earth or the stars? The fact that it is the Earth which is rotating can be demonstrated by means of a pendulum. If I set a pendulum swinging, it swings back and forth in a plane. Now, it turns out if this pendulum were at the North Pole of the Earth, the plane of swing would remain fixed relative to the stars, but would rotate relative to the Earth. Now, I'll have to show you what I mean.
This pendulum is at the center of this turntable, which will represent the Earth. Now I'm going to start the table turning around in this direction. I'll put a black arrow on so that you'll remember. All right, start the rotation. The pendulum is at the North Pole of the Earth, and you are looking at its motion as you ordinarily do, standing on the Earth. The plane of swing rotates in the opposite direction from the rotation of the turntable and at exactly the same rate. Now look at it from the fixed camera, which will represent the frame of the stars. The turntable, the Earth, rotates, but the plane of the pendulum remains fixed. A pendulum used for this purpose is called a Foucault pendulum. You saw me start one at the beginning of this film. Let's look back again now. This Foucault pendulum drops sand as it swings. I think you can see the faint line where the sand trail began. The amplitude of swing is decreasing. The sand trail isn't as long now. But the important thing to see is that the plane of swing has been rotating during the half hour that we've been talking to you.